So for this series here, we are asked, does it converge or does it diverge? Now, this problem doesn't inherently stick out to be a geometric, harmonic, just a simple series. We could take the sum of and find if it really does converge or diverge, just finding the sum of all the terms in the sequence. But what I do notice is that we can do a couple tests. Now, you've probably learned divergence test, integral test, and comparison tests. All right, but this one, what we're going to do is we're going to say, okay, let's first take a divergence test. Okay, that's what you should do for every single series. If you have a series, do the divergence test. It's what you need to do every time. So the divergence test says take the limit as n approaches infinity for the sequence of your sums. So that looks like this. Take the limit as n approaches infinity for the sequence of sums. So if I plug in any n value, I'm going to get one part of the sequence of my sums. So I'm taking the limit of n minus 1 over the square root of n to the 6 plus 1. Notice that this is going to be an indeterminate limit because n is just going to be infinity minus 1. I don't care. That's taking pennies from a billion gazillionaire, an infinitenaire. Okay, this here, I take, to the 6. I don't know what that would be. You know, we have square, cube. I don't know what to the 6 is, but you take infinity to the 6, it's going to just grow. Even though it's infinity, you're going to take the square root of it. It don't matter. It's still infinity. So it's infinity over infinity. It's indeterminate. So we need to do L'Hopital's rule. Hopefully you are comfortable with that idea of the L'Hopital's rule. We take that rule and we say, okay, take the derivative of the top and the bottom. What do you get? So this is going to just be 1 on the top over, and then this junk, well, you know, when we evaluate it, will just be infinity. So it's going to be 1 over infinity. What does this tell us? Well, this tells us this is an indeterminate, or sorry, not indeterminate. It tells us that this limit evaluates to 0. And the divergence test says, well, that's indeterminate. Now, you don't know if you're divergent or convergent because my output is 0. Now, if it was any other value, we know it'd be divergent. But in this case, that's not the case. Okay, so we've identified that the divergence test won't work. You might be able to take the integral test. I don't really know. I mean, is it always positive, decreasing, and continuous? Maybe. It could be. I don't want to prove that. That's kind of hard to prove with this. I mean, I'm sure I could do it, but I don't really want to do that. So instead, what I'm going to do is I'm going to do what's called a comparison test. If this step for the integral test is too hard, immediately go to your other test. So let's do a comparison test. So for the comparison test, we need to find a function that is either greater than or less than this function always, never equal to. Or sorry, it can be equal to, it just can't go above the values in the range of this one or below it. Okay, so for the comparison test, let's kind of transform our function here. Now, the way that I go about this is I say, okay, can I manipulate this in any way to get it to look a little different? Because I notice this and I'm not going to immediately see any function that might be similar. There is a rationale you could use. We might get to that. We'll get to that in a second. But let's do a little bit of manipulation. So I'm going to say, okay, this is really like saying this. Do you agree that that's true? Because remember that radicals, you can split them apart into two separate components, n square root of n to the 6 plus square root of 1. That simplifies to 1. Now notice our exponent here is a square root to the 6th power. This is really like writing 6 over 2, which is really like writing n to the 3rd. Okay, so we're going to simplify this too to n to the 3rd. Okay, now you should be able to see maybe a function that, or a sequence that might be a little bit different. Okay, if I get rid of these plus and minuses of 1, that's a shift. Now, if I get rid of a shift, what that's going to do is it's going to either raise or lower my function, if you think about it as a function, and it will just leave us with these, which is going to be always greater than or always less than our other function. So if I say this is n over n to the third, which I could say, I could rewrite as this. And I'm going to rewrite it as 1 over n to the second. If we think about what's going on here, actually, let's even just compare this one. It's a little easier to see. Which one's the greater function? Now, think about this function. What's different? Well, it's the -1 and the +1. Now, the -1 is saying, I'm going to make the numerator less valuable. When we add to the denominator, it's saying the exact same thing. I'm making your overall value less positive. So what's happening here is you're getting a lesser value here and a greater value here for all values of n. So this is always greater than this one. So we'll say that here as well because it's just a simplified form. Hopefully that idea makes sense. We're just getting rid of shifts that make this thing less positive than this one. So now that we know this, let's graph our function and identify what's going on to see if the comparison test worked or not. Because if the comparison test didn't work, there's no point, okay? There's no point in evaluating anything else. Sorry, we'd have to go to the limit comparison test, and yeah, we couldn't go anywhere. Because if this was greater than function, it diverges, well, this is not going to tell us anything about this one. It could diverge or converge, we wouldn't know. Sorry, I kind of had a little bit of a brain fart there. But this function, 1 over n squared. What do we know about 1 over n squared? Well, you could say that it is convergent because of the p-series. The p-series states that if we have an exponent greater than 1, not equal to, but greater than 1, this is going to converge. Okay, but if it was less than 1 or equal to 1, it would diverge. Now, this is actually really convenient because if this is always greater, let's graph this one as a green function and this one as a blue function. I'm going to say that this is always going to converge. So let's say it converges this way. It's going to go down, and it's going to converge to a singular value. This one is always less than. So that means that it has to stay, it's bounded above by this, so it needs to stay below it. So it could do whatever it wants, really, but it's going to converge below this one as well. It's not going to just cross the line and go to infinity. No, that's not what's going to happen. It's going to stay below the line, which means it won't diverge into infinity, it's going to converge. Now, what does this mean? Because this one is convergent, the comparison test tells us this is also convergent. Hopefully that idea makes sense. Now, that about sums it up for this video. We know that this is going to be convergent. We're not asked to find a sum. We're just asked, does it converge or does it diverge? Now, that's the work, and we used the comparison test to find that. I hope you guys enjoyed this video. If you did, please drop a like, comment, and subscribe, and I hope that you have a wonderful day.